Assalamualaikum and welcome back. Let's continue with example 1. So in example 1, we are asked to find a vector valued function to represent the intersection curve between the hemisphere z equals square root of 4 minus x squared minus y squared and the parabolic cylinder y equals x squared. Okay, so here we have two surfaces. One is a upper hemisphere and the other one is a parabolic cylinder. So let's sketch this. We don't have to sketch it, but just for the fun of it, let's do it anyway. So we have the x-axis, z-axis, and the y-axis here. I'm going to sketch the two surfaces. We don't have to, but just for the fun of it, let's do it. Here we have the z-axis, z-axis, x-axis, and y-axis. Okay, for the first surface, z equals square root of 4 minus x squared minus y squared, that is a upper hemisphere because we have the positive root and the radius of the sphere is 2. So let's say this is a 2, this is negative 2, a 2, and this is also a 2. So we have the upper hemisphere. I'm gonna sketch this real quick, and here we have 1, 2, 3, 4. Here, that's a 2 as well. Okay, and then we have the parabolic cylinder. So in 2D, that's a parabola upwards. But in 3D, that is a parabolic cylinder. So let's say this is a negative x-axis. So for parabolic cylinder, in the equation, as you can see, it doesn't have z in it, meaning that it doesn't matter what z is. We have the same shape of parabola. So when we connect the two, we get a parabolic cylinder. When we connect all the parabolas, we get a parabolic cylinder. Now, when these two surfaces, the parabolic cylinder and the upper hemisphere, intersect, what we have is a curve. So the curve maybe look like, I don't know, let's see. It's on the parabolic cylinder and it is also on the upper hemisphere. So the green curve is the intersection curve between the two surfaces. Okay, now our task now is to represent the curve using vector valued function. Okay, so remember what we need to do is we need to introduce parameter t that can relate the variables x, y, z on the two surfaces. Okay, so what we do is we start with the surface with less variable in it. So in this case, the surface that has less variable in it is the parabolic cylinder. We have y equals x squared, so we're going to use that. We're going to start with that. Okay, let's say we let x equals t. Okay, so we introduce a parameter t here. So if x equals t, then y here is x squared. But we already represent x as t, so from here we get y is going to be equal to t squared. So now we have relate variable x with the parameter t, and we also relate variable y with parameter t. So the next task is to relate z with parameter t. So we continue with the second surface, which is the upper hemisphere. So on the upper hemisphere, we have this equation, z equals 4 minus x squared minus y squared. Okay, we already have x in terms of t, so we have 4 minus. So replace this x with t, so we have t squared. And replace this y with t squared, then we get minus t to the power of 4. So now we already represent, or we represent x, y, and z with the parameter t. So now we're just gonna write them all together. So remember, for a curve in space, we can represent it using set of parametric equations. and we can also represent it as a vector valued function. Okay, let's write the set of parametric equation first. So the parametric equation, the set of parametric equations of the intersection curve would be x equals t, y equals t squared, and z is equal to the square root of 4 minus t squared minus t to the power of 4. Okay, and we can also represent the intersection curve using vector valued function. So the vector valued function, or for short just vector function, of the curve, intersection curve between the two surfaces is, let's call it R. Okay, so remember, for vector valued function we have the x component, the y component, and the z component. Okay, let me refresh your memory on that. Okay, so the x component of the vector function is really the parametric equation for x. The y component is the parametric equation for y, and the z component is the parametric equation for z. Okay, so we already have the set of parametric equations, so now we're just going to put them together. So the x component now is t, so we have ti. The y component, just use the parametric equation for y, we have t squared j, and the z component would be the parametric for z, which is the square root of 4 minus t squared minus t to the power of 4k. Okay, alright, so there are two ways of representing the intersection curve. We can use the set of parametric equation like so, or we can use vector valued function. Thank you.